Good afternoon, students. Welcome to today's session on digital electronics and microprocessors. In today's session, we shall discuss about the memory systems. These memory systems are very useful because they store the information that can be used at a later time. What are the memory systems, what are the different types of memories, and we shall discuss about each and every detail of some of the memories called the core memories and the semiconductor memories. So, we shall begin with the memory systems. In today's session, we shall discuss the topics that are put into two categories, the magnetic core memories and the semiconductor memories. As part of the magnetic core memories, we shall discuss about the magnetic core as a storage element, the 2D array of magnetic core, the coincidence memory, and the basic principles of the magnetic media such as the magnetic disc, magnetic drum, and the magnetic tape. We shall also see the semiconductor memories, the ROM, the RAM, EEPROM, and also we shall have a little discussion about floppy disk and hard disk, which are the most widely used memories in our day-to-day computers. We shall also see certain recording techniques called as the digital recording techniques that are useful in today's modern storage media such as the CDs and DVDs. So, we shall start with the definition of a memory. A memory element is a storage location of information so that this information can be used for use at a later time. This memory is essential because the programs that we run are stored in memory, and from time to time we are going to load these programs to the required location. Upon running these programs, we save these back into the memory locations. So, as such, the memory is useful to us as a safe bank where we can use the data at the required time, and we can also see that the data is stored in a disciplined manner. That is, the data is stored in addresses so that we can access to the required data by simply accessing the address location based on the address. So, as such, these memories are very essential in the digital electronics applications. As part of these memories, the magnetic core memories are the older versions, whereas the semiconductor memory is that of the modern day usage. We shall study about these two memory types in this session. The magnetic core memory is one of the most first types of memories used in applications. Of course, these types of memories are outdated today. Anyhow, the study of these memories gives us a good idea as if how later versions of memories were developed. Hence, we shall see how a magnetic core is useful as a storage element. As you know, a magnetic core is a magnetic material such as steel or iron. When this is placed above a current carrying conductor, or this conductor is wound on this core, flux will be passing into this core. That flux will be stored, and as you know the hysteresis loop, the amount of the degree of magnetization of the magnetic force contained in this core will depend on the magnetization force H, which in turn depends on the strength of current flowing through this coil. So, this is the hysteresis loop that you know. This is the magnetization force, and on the y-axis we are plotting the degree of magnetization. This hysteresis loop says that there are 2 points, you can see here the point Q and P, which are supposed to be the stationary points, and any point in between will be leading to the final point P or Q. So, as such, if you apply a current which is only half required to produce this final degree of magnetization, then this will lead to P. Similarly, a total current flowing in the opposite direction, say plus Im, will lead to storage of a degree of magnetization which is positive in nature. So, this is the hysteresis loop based on which we shall continue our discussion. You see, in this first core, the current is passing in the direction from left to right. The magnetization field produced in this can be treated as a binary digit, say here the digit 0, or if the current is sent in the opposite direction, then automatically the flux developed will also be stored in the opposite direction. Hence, that degree of magnetization minus B can be treated as other binary level, say logic 1, that is the direction of the stored magnetic field depends on the direction of current. If we see at the previous hysteresis loop, here a positive current is resulting in a positive degree of magnetization, and a negative current, in the sense the current flowing in the opposite direction is going to result in a degree of magnetization of minus B as such. So, in binary notation, this can be treated as the positive degree of magnetization plus B can be treated as storage of a binary data 1, and the opposite, the minus B, as the binary data bit 0. Now, we shall see how this is useful in real time applications. The previous one was only a concept, and this core used is the real time core used in memory applications. Here you can see many number of coils. The coils X and Y are the actual coils carrying the currents. The combined effect of these two magnetic fields will result in a magnetization force inside this coil. So, the overall effect will be to store a positive flux plus B or minus B. This coil S is called as a sensing coil, and the use of this we shall discuss at the time of discussing the reading of data. The coil Z is useful to see as to what binary bit is to be stored or at the time of writing of the data. So, a core consists of 4 coils, 2 for the flow of current and the other two in order to see whether writing or reading is to be done. As such, the core is initially a non-magnetized material. Once currents are sent through this coil X and coil Y, the currents will develop magnetic field, and that will store the degree of a magnetization force inside this core. To store a binary bit 1, we have to send a current of I max by 2, that is plus I max by 2 through the X coil, and a similar amount plus I max by 2 through the Y coils. The combined effect results in a degree of magnetization of plus B that will be treated as binary 1. In contrast, if you send simultaneously a value of minus I max by 2 or a current in the opposite direction through X, similarly a current in this direction in Y, the combined effect will cause a magnetization force that is stored in the opposite direction. That will be treated as the binary bit 0. So, this is how the magnetic core will be useful to store the binary bit 0 or 1. This single binary bit is not useful for us, hence we will use multiple cores such as matrix, so that a bit or word can be stored at once through an array. You can see here an array of cores placed on this stack. To store, you can see here one particular core which is a little darker, and in order to store a binary bit 1 inside this, what we have to do is send the currents I max by 2 through this Y coil and through this X coil. Now, you may say that simultaneously other cores are also getting these currents, that is, all the cores that are in the same row as that of this, that is, the cores this and this are getting a current of I max by 2, but why are they not going to store the information? They do not store the information because simultaneously the current through the Y coil connected to them is 0. So, only those coils through which simultaneously the X coil receives a current of I max by 2 and the Y coil receives a current of I max by 2 will result in storage of data. Hence, as though the cores in this row and also in this column get I max by 2, they do not store the data. Only this stores the data because it is simultaneously getting I max by 2 and I max by 2. So, that is how we store the bit in the required location in an array. Here we have seen a 2D of the storage elements. In fact, in practicality a 3-dimensional array will also be used, but that is very complex to show here. Hence, we shall discuss only the 2-dimensional array. How we have to store is, we shall, I remind you, send a current of I max by 2 through each of the X and Y wires simultaneously. The combined effect results in plus I current and creates a magnetization of plus B. In the other cores, it is only I by 2, hence in these cores it is only I by 2. Similarly, in these cores it is only I by 2, hence there is no magnetization stored, hence the binary data is not stored. Here you can see this is the stack of cores used in real-time applications. You should see very carefully. Here is one core and here are coils running through each of the cores. Since there are multiple cores and multiple wires, this may appear to be a complex picture, but in reality this complexity does exist. So for clarity, you can have a glimpse for a while. Look at this core. It is a core, it is a core, similarly core, as such they are placed in rows and columns. Wires, you see dark lines. These lines are nothing but the wires, the X and Y wires passing through the cores. So this is the stack of cores used in real-time applications to store huge quantity of data, because in real-time applications we do not store a single binary bit or a simple word like byte. In fact, we use kilobytes and megabytes. To store such huge quantity, so many number of cores should be used. Then how to write and read the data into these cores? This is called as a coincidental memory, because there should be the coincidence of the currents passing through the X and Y coils. If only X is flowing or only Y is flowing, it will not cause storage of information. Hence, those coils are called coincidental coils. The memory made up of these is called as coincidental memory. You can see here 4 cores and a data bit of 1001 is required to be stored into this. Here I have shown these cores where I want to store 1 as a little darker and those where I want to store 0 a little white. So here to store 1, you know that simultaneously you have to send I by 2 and I by 2 through X and Y wires. So see here, this is the X wire running through all the cores, and you can also see the Y wire which is placed in diagonal to the X wire. This is the Y wire passing through all the cores, and at each time it is at right angles to the X wire. So the combined effect of these two will create a data storage of 1 and 1 in all the cores. But the data we want to store is 1001 but not 1111, as these currents are passed through all the cores. There is a possibility that all will store 1, but we want to store only zeros through these. For this purpose we use the Z coil. You can see here the Z coil, right? Whereas in those cores where we want the bit to be stored as 0, you have to connect the Z coil also. The Z coil runs parallel in the plane of the X axis, but at all times it carries a negative current as that of the X. That is, the direction of current flowing through the Z coil is opposite to that of the X coil. Hence, you can see here it is passing here, X is passing current. See here, X coil is causing current to flow like this, whereas the Z coil is causing current to flow in the opposite direction. See here, in this line, blue line, the Z current is flowing, whereas in this red line the X current is flowing. So in this core the two currents are flowing opposite to each other. Similarly, in this core you see the X coil is coming and it is flowing the current from left to right, this red wire. In this current flows from left to right, whereas the current flowing through the Z coil is flowing from right to left. So, what is going to be the combined effect? In the coils where the Z current is not flowing, that is in the topmost core and also in the bottommost core, you know that only X and Y are the currents flowing, and hence data bits 1 and 1 are stored. Whereas where Z is also flowing and it is carrying a current of minus I by 2, the combined effect is that this minus I by 2 plus the existing I will reduce the overall magnetization to plus I by 2. This plus I by 2 is not treated as binary 1. Anything less than plus I will cause only binary 0 to be stored. Hence, by passing a negative current through the Z wire, we can accomplish the writing of 0 bit through these cores, whereas without connecting the Z wire in these two cores, it is possible to write the 1 bits. When we want to read the data, we have to use the sensing wire S. This wire also passes through the core. As you know, during reading of the data, the X and Y wires do not carry currents. Rather, the existing magnetic field has to send current pulses through the sensing wire. Hence, we have not shown the X and Y wires, rather the sensing wire S is placed. This will be used to pass a current pulse to the output. In order to read the data, a current of minus I by 2 should be used instead of plus I by 2. The currents minus I by 2 should be used through the X and Y wires. This results in change of magnetization in the core. Suppose that this core previously holds a binary bit 1. Due to the flow of minus I by 2 minus I by 2 put together minus I, suddenly the magnetization in these falls from plus H to minus H. This sudden change through this coil will cause a current pulse to be produced through the sensing wire. You know, when there is a relative motion between the magnetic field and the current carrying conductor, currents will be induced in this. Since this conductor is stationary and an instantaneous change of magnetic flux is taking place through this core, that results in a current pulse S to be produced in this coil, in this core. Whereas in this core, which was previously storing a data bit of 0, what happens when you send these currents minus I by 2 and minus I by 2 through the X and Y wires? Since this was previously holding a magnetization force of minus H, the passage of negative currents will not change the magnetization in this core. Hence, there is no change in the magnetic flux. There is no motion of the coil. Hence, current will not be produced through the sensing wire. So, the sensing wire will give current pulse for only those cores which were holding a binary bit 1. There is no current through the cores, through the sensing wires connected through the cores which were holding binary bit 0. As such, a sudden change of magnetization will cause current pulses through the sensing wires. This is how we read the data in the two-dimensional course. Here, a write-back mechanism must be there once the data is read, because here you see in the previous case, once we read the data, the data which this was holding prior to reading was 1, but upon reading the data it lost and it has become 0. So, should we lose the data upon reading? In that case, each time we read the data, it is very dangerous for us because the data is lost. For this, there must be some mechanism called as Rightback mechanism. This mechanism sees that upon reading the data, the previous content should be restored through the course. So, that is called as the Rightback mechanism. This should be used to restore the magnetism lost in those bits that were previously holding the binary value of 1. That is about the magnetic course. Now, where we use and what are the applications of these magnetic storage elements? This magnetic drum memory is one of those applications of magnetic storage of data. See here you can see a drum. It is a cylinder placed and here are chassis. This cylinder is having storage elements called cells along its periphery. So, along this it has cells and cells as such, and read write heads are placed along the entire periphery of this drum. See here, for each track there is a read write head. So, as such, when the drum rotates, these read write heads will receive the information contained in that particular cell. The magnetic drum consists of a cylinder coated with magnetic medium, and that medium is divided into tracks. A large shaft here, this shaft consists of the read write heads, one head for the first track, second head for the second track, as such. It consists of the read write heads for each track and it moves over cylinder. If the cylinder is to move, then these heads remain stationary. Then the reading or writing of data is simultaneously done in multiple tracks. You can see here it is divided into 1, 2, 3, 4 as such tracks, and each read write head will simultaneously collect the information at that particular position on that particular track. Thus, reading of huge information is simultaneously possible. That is about the magnetic drum memory. But this magnetic drum memory is outdated today. Now, we shall see one of the more familiar, the magnetic tape memory. This is a huge storage medium. It is an endless medium. For this, we have to see the basics of magnetism. In a ferromagnetic material, in general, a material such as iron previously remains unmagnetized because these small molecular magnets are put in random fashion. So, suppose that this is the north and this is the north and this is the south pole, then it will behave as a magnet only if they are properly oriented, else the north pole of one will cancel the magnetization of its adjacent one and results in non-magnetism. In a tape, we use this kind of a track. This is only one cell. These two blocks put together forms a cell. Now, this stores the information as such. If two tracks, if two blocks that are adjacent to each other are oriented in a similar manner, then the data bit stored in this will be treated as bit 0, whereas if they are oriented opposite to each other. You can see here all north poles are oriented to the left in the left block and all north poles are oriented to the right in the right side block. Hence, the overall data contained in this cell will be treated as binary 1. Now, we shall see the semiconductor memories. Basically, we have two types of semiconductor memories, the read-only memory and the random access memory. The read-only memory contents will remain forever, that is, they are not disturbed due to power failure, whereas the contents of random access memory will be lost once the power is off. This is called as the volatile memory. Also, that you cannot write the data again in this read-only memory, whereas a new data can be written on the existing location in a random access memory. The further division of these two memories is the bipolar ROM and the MOS ROM. The bipolar ROM uses the transistors, whereas MOS ROM uses MOSFETs. Similarly, the RAM uses static and dynamic types. The dynamic type of RAM requires frequent refreshing of the data. These two are made up of the MOS cells. This is the basic ROM. It consists of an array and it is divided into rows and columns. These rows are selected by using an address decoder. Suppose that I want to read the content of row number 1. The decoded address, this address decoder will select this file. Hence, the currents contained in this D3 column will be read as the data. See here, upon selection of this wire 1 is not connected to D3, hence there is no current through this. Similarly, D2, whereas here it is connected through the diode to the D1 line, hence this data will be stored as binary 1, it will be treated as binary 1, hence the current will flow from this into this. The resulting of this will be a binary 1 here. Similarly, there is no connection between this row and the column D0. As such, overall we can say that the row 1 contains data of 0, 0, 1, 0. As such, by knowing the address, we can read the data contained in a specific location. This is the read-only memory. This is the random access memory. Here, it is a bipolar type of RAM. It is made up of two multi-emitter transistors arranged back to back so that it forms a flip-flop. You can see here by connecting the power to these two through the collectors, and multiple emitters are used. The output of, say, this transistor is treated as the content stored in this cell. You can choose any transistor, but for our discussion we shall treat that the output voltage of this transistor will be treated as the content stored in this cell. Since this is a back-to-back connection, at any time only one of these two transistors will be on and the other is off. If a given transistor is off, that is, if it is in cutoff condition, then its output voltage, that is the collector voltage, will be equal to VCC. That we shall treat as binary bit of 1. In contrast, if the transistor is in saturation, say on, its collector voltage will drop to 0. That we shall treat as the storage of binary bit 0. Here the multiple emitter leads are used for different purposes. This lead, the outer emitter leads you can see, which are connected through this yellow wire, are used for column select, whereas the middle emitter leads through the orange wire are used for the row selection. Since the cells are placed in an array, the specific location of this cell can be known by selecting the row and a column corresponding to this particular RAM cell. For this purpose, we use the row select and column select signals. Here the green wires are used to give the read or write sensing signals. We shall see how to store the data and how to retrieve the data, that is reading and writing of data through this bipolar RAM cell. To read the data, suppose that you put the read oblique write wire is made high. In that position, what is going to happen? Suppose that the previous content is 1. The content will be 1 only if this transistor was previously off, that is, this was in cutoff condition. When we connect a read signal of high, it will not sense any emitter current because this transistor was previously off. When the previously stored content was 0, this transistor must be in saturation. In that case, a current flows through this as soon as the read is made high. That is, once the read signal is given, if the previously stored content is 1, there is no current through the sensing signal, or if the sensing methodology is by using a voltmeter or through a sensing amplifier, in the sensing amplifier there will not be any current. If the stored bit is 0, there will be current flowing through that particular sensing amplifier. This is something opposite to the 1 and 0 stored, because negative logic must be used in all these circuitries. So, if current is flowing in the sensing amplifier, it is equivalent to reading of bit 0. If current is not flowing, it is equivalent to reading of bit 1. Now, how to write the data? To write the data, you select the particular RAM cell by using these row select and column select signals. Since these wires are connected to all the cells along the array, only that particular cell to which both row select and column select signals are high will be selected. Its adjacent cell will not be selected because for that either row select or column select may be high. Hence, to get random access, that is to go to that particular cell we want to write the data, you have to make the row select and column select signals of that particular location as high. Once this particular cell is selected, you have to make the right signal at this particular wire to be low. Previously for read we have made it high, whereas for write we have to make it 0. Once this is made 0, the condition at this place depends, the bit written will depend on the condition of the read and write emitter point in the other transistor. To store a bit 1 over here, we should make this transistor into cutoff condition. That can be done by making this into saturation. So, you apply a high signal at this transistor emitter point. Once it is made high, this transistor will be driven into saturation. That causes this transistor to move into cutoff condition, and hence this will be equivalent to storing of data bit of 1, because in cutoff condition the output voltage VCE will be equal to VCC. Hence, this transistor which is in cutoff is said to store a binary bit 1. To store the bit 0 in this transistor, we have to first make the right signal 0 and then apply a low signal at the other transistor end. This causes this transistor to be driven into cutoff condition. That causes this to move into saturation. Once it is in saturation, the output voltage will be low. Hence, it will be equivalent to storing of binary data 0 in this RAM cell. This is how we read and write the data in RAM cells. This is a programmable ROM. At first, all the cells are available. By programming, it means that the diodes at required positions are retained and those not required will be fused. Suppose that in the row 0, I want to store the data 0, 1, 1, 0. So, at first this entire structure is available. Out of this, since I want 0, 1, 1, you retain these two diodes, 1s and 1s, and fuse these two diodes, the first diode and the fourth diode. This causes storage of the data 0 in the two outer diodes. This is once programmed if the bit supposed to be 0, 1, 1, 1. The applications of the magnetic memories will be in the floppy disks, wherein the cells are stored along the tracks, and for our facility in reading and writing, it is divided into sectors. Read-write heads will be sensing the content. Between these two read-write heads, the disk will move. This is the read-write head, and below this the disk moves. This can move laterally also. This is how sectors are formed, and what do you mean by a track? This is how higher units called as cylinders are made up of. A full track will be treated as a cylinder, whereas a part of it will be treated as a sector. The optical device, the compact disc, uses the digital technology. Here in the digital coding techniques, first the layer is placed, an optical sensitive layer is placed on this disc, and laser beam is passed onto this. Wherever the locations are exposed to the laser beam, at those places data will be stored, and where the beam does not fall, it will be treated as bit 0. This is how the data is stored in various memory units. So, students, till now we have seen the various memory systems used in the digital electronics. Out of these, the core memories are huge memories that are now outdated, whereas the semiconductor memories are that are there in real time applications. Once you open the motherboard of your computer, you can see an EEPROM as a chip and a RAM as a card. You can see various memories inside the computer, and also when you visit the microprocessor lab, you can see the EEPROM in which we load the program. So, this is about the various memory systems. Thank you all.